Okay, so let's talk about an application of this stuff we've been discussing. This idea of half-life versus decay rate, and the the modeling of exponential decay in particular. This is going to be radioactive decay. Carbon-14 is an example of a type of radioactive element, and it is a half-life of 3,730 years. And so we can use the mathematics we're learning in this section to like explore how scientists use carbon-14 to determine how old some sort of very old object is. There's a lot of stuff in this that I'm going to kind of glaze over, and I'm going to focus on just like the math and the application of the formula I've shown you. I'll try to explain a little bit of the rest of it, but I am also not actually a physicist, so I don't really have an in-depth understanding of how this works. I have a cursory understanding of how this works. So, first of all, carbon-14 has this growth rate. This half-life. So let's calculate the growth rate, or the decay rate. Sorry, I keep saying the wrong word. Decay rate, given our formula, k is going to equal negative natural log of 2, or alternatively the natural log of 1/2, divided by the half-life, so 3,730. So that we'll use that as our k value. I'm just going to use that exact expression so that it is exact, as opposed to approximating that to some number of decimal places or whatever. So now, given that, it means that the quantity of carbon-14 is going to be given by the function f of t equals whatever the initial quantity was times e to the power, and this is our k value, so negative natural log of 2 over 3,730 times t. Okay, and it's negative, right? Because this is decay, so the k value is a negative number. That'll be a negative number. So now, let's suppose that we have an object, some very old object. Let's suppose it contains only 20% of its original carbon-14 that it would have contained. How would we know that, first of all? Okay, so this is where I'm going to kind of give a rough explanation of how scientists can figure this sort of thing out. Basically, say the object is like a piece of clay or whatever. Then what scientists can do is look at the clay that comes from that area where that clay was found, where they expect the clay was sourced, and they can examine the carbon in that clay and check to see what the what the ratio of regular carbon to carbon-14 is, because carbon-14 is this particular radioactive isotope of carbon, and it occurs at this sort of particular ratio with the rest of the carbon. And it has something to do with, this is where I don't really like know all the details. It has something to do with the ratio of carbon-14 to carbon-12, I think it is, in the atmosphere. And so we can figure out what the ratio should be and what the ratio would have been, when that thing was made. And so then we can determine that now it has some, we can determine that it's got just 20% of its original carbon-14. Okay, so there's all sorts of science involved in determining this information. But once we have this information, the way we can use our model to figure out the age of the object is to say, well, we don't know the initial quantity, and it doesn't really matter. A0 is the initial quantity, but we don't even need to know that, because what we have now currently is 20% of A0. So that would be 0.2 times A0, right? This is 20% of the initial quantity. And that's what we currently have. That's now. So let's set that equal to A0 times e to our negative natural log of 2 over 3,730 times t. So that's our model. And the t value here is going to be the number of years